oxidations to cover the material which we make for this. Now, let's talk about this part first. Should have had this up there, my fault. Alfred Werner, so-called father of coordination chemistry, because he's given credit for recognizing that the coordination phenomenon was something that chemists had not yet thought about when he did the work that he did, and recognized that there were no theories as yet available which could explain his observations. A brief account. Cobalt chloride with cobalt in the +3 oxidation state. Dissolved in water, no more, no less. Observe the evolution of oxygen. Now that means redox. That means water is being oxidized. And the only possible material which can oxidize water is what? Anti-chloride ion, that's in the -1 oxidation state. So it has to be cobalt-3. Indeed, after the oxygen evolution stopped, he evaporates the solution of dryness, and instead he gets cobalt in the +2 oxidation state, but he doesn't get just cobalt chloride, he gets cobalt chloride with 6 moles of water per mole of cobalt. Repeats the experiment. Only difference is in the second investigation, he dissolves the cobalt-3 chloride in 6 molar ammonia solution. Water is still, of course, the abundant material, principally abundant. Now, no oxygen evolution. Evaporates the solution of dryness. Cobalt is preserved in the +3 oxidation state. How would you recognize this? Well, analysis of this would show 2 moles of chloride ion per mole of this compound, whereas this shows 3 moles of chloride ion per mole of this compound. But unlike this, where we have 6 moles of water per mole of compound, cobalt-containing compound, now 6 moles of ammonia. Solid state, water, solid state. Something very interesting and important is going on. Water and ammonia by themselves under normal act conditions. Liquid phase, vapor phase. Yeah? I'm doing this simple investigation to isolate the material where water is part of this compound and clearly solid state. Solid phase. Ammonia, not vapor phase in the compound. Solid state, solid phase. And why no redox? Reason. Somehow, someway, cobalt in this system has got to be prevented from reaction with water molecules. Accounting for no oxygen production. What's the reason? Coordination. Now, I doubt that Werner thought of the term or coined the term, but if I use a model, because we now know that in the first material, cobalt is octahedrally complexed by water molecules. In the second compound, cobalt is octahedrally coordinated by ammonia molecules. Tell me. Based on the observations made for the first reaction, since chloride ion and water molecules each are now known by us to be capable of functioning as monodentate ligands, because of non-bonding electron density in the valence environment, would you expect water molecules or chloride ions to bond more strongly with cobalt-3 or cobalt-2? Don't be hypnotized by my rotating dish. You're supposed to be thinking by answer. Well, what bonds more strongly with silver ion? Water molecules or ammonia molecules? Ammonia molecules. What bonds more strongly with silver ion? Ammonia molecules or chloride ions? Chloride ions. What bonds more strongly to H plus? Water molecules or ammonia molecules? You know this. Ammonia molecules. Chapter 18. What bonds more strongly to H plus? Water molecules or chloride ions? Water. Well, look at that. These damn chloride ions are minus things, yet water molecules bonds more strongly. What bonds more strongly with H plus? Ammonia molecules or chloride ions? H plus. Ammonia molecule, much more strongly. Chloride ion doesn't even get in the game when it comes to competition for Cl- in water solution. We know this. But if you change this plus species to silver ion, then chloride ion wins the game, doesn't it? What does this mean? That means the strength of the interaction between the Lewis acid and the Lewis base depends on both of these species. So, from this first result, we can recognize that which material, water or chloride ion, apparently wins the bond strength formation game with chloride ion. Which one? In this first material. Is it true that in this first material, water has to react with cobalt? Hey, how else would I get oxygen? You think I'd oxidize this small load? You think I'd turn this into coke from cobalt and carbon monoxide? Come on. That's a lousy chemistry joke. When I isolate this material, what do you think is the structure of this material with respect to cobalt and the water molecules? Think I might be showing you it? Where each of these spheres represents a water molecule? And the chloride ions are only connected to this material by Coulombic contraction. And in this case, the coordinate covalent bond is stronger than the Coulombic contraction, isn't it? Hey, the facts speak for themselves. Now what about the second case? In the second case, water doesn't get the game. So what seems to make stronger bonds with cobalt in the +3 oxidation state? Is it water or ammonia? Ammonia. So, it seems to be the case that as the positive charge density of the positively charged species increases, in this case that's cobalt, the sigma bonding strength of ligand determines which ligand will interact with the species. Just let the facts speak to it. Silver plus, hey, chloride ion wins. Cobalt +3, ammonia wins. And when ammonia wins, ammonia is surrounding cobalt in the +3 oxidation state. Now imagine every one of these groups is an ammonia molecule. And there's no stick here in space. These things are all snuggled into. The valence shells of cobalt. All the ammonia molecules that through the nitrogen atom are in contact with cobalt. The valence electron clouds overlap. Oh, and these ammonia molecules are wrapped around cobalt-3. In essence, protecting cobalt-3. Can the water molecules even get in there to make contact and engage in this redox reaction? No. How about that? All because cause of coordination. Now, back to ligands. You talked about ligands rather extensively in discussion class this week. I want to add a few comments. These species, as you know, are monodentate ligands, capable of making one sigma-coordinate covalent bond, no more with any particular metal ion. Even though this, for example, has got 2 non-bonding pairs, and this, for example, has got 4 non-bonding pairs. Hey, you know what the geometry is of a water molecule. Here. Water molecule. Hydrogen, hydrogen, oxygen, 2 non-bonding pairs. Well, if this non-bonding pair makes a coordinate covalent bond with a metal ion, like B, or my hexametal ion, look at the directionality in space of the other non-bonding pair. It's pointing in a different direction. It cannot also interact with my noggin. It can interact with something else. And if it does interact with something else, this is said to be a bridging ligand, because it interconnects the 2 centers of positive charge. And there's another metal ion over here, another one of my noggins. And you probably say, oh, God, 2 more. Same with chloride. Those are sp3 hydride atoms. Non-bonding pairs are, from a geometric standpoint, separated in space from each other by 109.5 degree bond length. Now then, how about this novel ligand? Ethylene diamine, which is capable of making 2 coordinate covalent bonds, the same metal ion at the same time. So it's said to be bidentate. Bi-2-dentate. How many bites can I make? Which is what transitional chemists first started to call this coordinate covalent bond formation interaction. A bite, dentate, the ligand taking a bite out of the valence environment of the coordinated metal. Now this is rather a condensed little structure. As I've shown the H2s immediately attached to nitrogen with a bond and an H and a bond and an H and a bond and an H bond and all that stuff. What's the shape? What's the geometry of this thing? This ethylene diamine bond. This look like it. There's an NH2 group right there. There's the other one. That's the other molecule. These black tetrahedrally shaped parts are the carbon atoms. And all I can find available to simulate hydrogen atoms are these blue things. And all the skeletal atoms are connected to each other by single bonds. As you learned in 2045 that along a single bond axis, the groups connected to each other can rotate in space in opposite directions without breaking the bond. But as soon as you get multiple bond character at any covalent bond site, what happens to this free rotation? Disappears. Can't do it. So there's one method by which in the laboratory we can observe whether a covalent bond is single or multiple in character. Well, because of this rotational freedom along each of these skeletal atom single bond axes, notice that with this rotational configuration, I've got these non-bonding pairs pointing at the same place in space. So if again my metal atom, my noggin is a metal atom, right? I get bidentated. I get chelated. That's a name for this. This shows you one of my famous Easter bonds. Hey, how many atoms in this Easter bond that I have? How many atoms in this ring-shaped thing? Oh, pardon me, I should have said, how many atoms in the ring? That's my perfect language. How many? 5. My noggin, 2 nitrogens and 2 carbons. Keep that number in mind, because we shall develop an argument which will show you that rings which contain fewer atoms than 5 rarely, if ever, form. Rarely. And I don't know of any stable chelate rings which are 4 atoms, although there may be some. But I know if they are in existence, they're not particularly stable. There's another example of a bidentate ligand. It's the oxalate ion. OX is shorthand for the oxalate ion, and perhaps from our acid-base table, you recall this formula appearing in the table, although in our table I probably wrote it like this. Try to give it structural character as much as possible. But when you see this formula, you can recognize there's no oxygen-oxygen bonds, and that's difficult. You need to know some chemistry to know that there's no oxygen-oxygen bonds in this. Gentlemen, if I told you, which I just did, that chelate rings with 5 atoms are stable, also with 6, 7, and maybe with 8. When you start making the ring too large, for other reasons, they're not stable. The reason in the main for instability of large rings is called steric hindrance. What's steric hindrance mean? It means you can't put 2 things in space where there's only enough room for one of the things. Steric hindrance relates to what? You can't get 300 students into a phone booth unless it's a damn big phone booth and the students are damn small. Such is usually not the case. Getting 400 students into a Volkswagen Beetle. There's not enough place in that space. They sterically hinder each other. These are physical entities. They have volume, and they block each other up. So the middle line, general formula Mn plus, is to react with this, the oxalate ion, and make the chelate ring. Notice the middle ion in solution can approach the chelate ring from this side, this side, this side, this side. Which of these sides do you think would lead, which of these directionalities of attack do you think would lead to stable chelate ring formation? Here or here? Here, west to east. Here, south to north. South to north, because if the middle ion winds up here, then I get a chelate ring. A bond here, and a bond here, and a 1, 2, 3, 4, 5 atom ring, a stable ring. Next, when I take away the ion, it has a chelate again. What valence electron property shown by this species? As it is. Now let's chelate. This non-bonding pair is no longer a non-bonding pair. This non-bonding pair is no longer a non-bonding pair. What happened to this charge? Not there anymore. It's transferred to the metal ion. Resonance? Still present? As if by magic. Before the bond, the carbon-oxygen bond lengths and strengths are equal. Shorter, stronger, CO single bond. Longer, weaker, CO double bond. But as soon as I coordinate, this bond gets shorter and stronger, like this bond, and this bond gets longer and weaker. Interesting. Now, how about this ligand? Do you think this ligand could function in tridentate capacity? 1, 2, 3. Well, you invited to think further about this like behaving in tridentate capacity when you play with these. Please don't fall apart. This look like it? There's my central nitrogen. This nitrogen, I ran out of blue parts. 3 non-bonding pairs. And if each adjacent nitrogen bonds to the same metal atom or ion, how many rings do I need? Really fancy Easter egg. How many rings? 2 rings. And in each ring, how many atoms? 5. Do you think this is stable? Do you think this is more stable than this single ring? Why would you expect this with 2 chelate rings, each of which contain 5 atoms, to be more stable than the chelate with the single ring with 5 atoms? But simple thermodynamic consideration would allow you to say this ring is probably more stable. More bonds. They're the same kind of bonds, aren't they? They're all sp3 nitrogens donating to the same metal atom. Hey, more bonds. You might wish to look up the ethylene diamine tetraacetate anion. Shorthand abbreviation name EDTA. Have you ever heard of EDTA? A while back, companies like Johnson & Johnson and whatever have you started selling materials which you would find among the shelves, at the shelves at Publix and whatever have you, stacked among these things for cleaning at home. The material to which I refer is the stuff that you would go and use in your bathroom, and after you take a shower, you spray it in the shower chamber. And it's supposed to help dissolve soap scum and things like that. So now by just water, you will turn the soap scum, which isn't water soluble, into soluble stuff by EDTA chelation. And you can rinse it down and use it, and use any of these products. When you use products like this, do you ever read the labels? Or you just happily believe these manufacturers are all nice, honest, upstanding people. They're going to sell you great stuff. Nothing to worry about. Hey, I don't trust anything. That doesn't mean I distrust them. But I don't trust them. I want to read what they're selling, especially before I buy it. EDTA is made by taking one of these ethylene diamine molecules and reacting it with an acetate ion. You know what an acetate ion is. That's why it's called ethylene diamine tetraacetate anion. So you take an acetate ion, which you know looks like this. And the synthesis that you do to remove one of these hydrogens from the CH3 group. And get it to bond with this nitrogen. Same here. Same here, same here. So you wind up with a ligand, a very fancy ligand, a very powerful ligand because of all the coordinate covalent bonds they can make with the same metal atoms. Bond here, bond here, bond here, bond here for another one of these. Another bond here, another bond here. It all wraps around and makes a geometry that is in essence what? What would you bet with 6 bonds? Would you bet octahedral? That's what it looks like. It's a pretty complicated structure, but you can look on the computer if you want, look on the internet, and you'll see pictures of complexes of EDTA, metal ion complexes of EDTA. One very common, which is calcium ion. Because materials at home that you have to clean up are often insoluble calcium ion materials, like sulfates, phosphates, and carbonates. You're familiar with materials like this, aren't you? That's what we talk about in class, what you've done in the laboratory. You know, the EDTA and complex these things, and we've already talked about rendering materials which are not very soluble into soluble materials by forming complex ions. Remember? That's chapter 19. That's what you do with EDTA. All right? Now we go to section 24.5. You'll see a collection of formulas listed there in the table. On this page, what's the page? Which is 146. And every one of these complexes contains platinum in the +4 oxidation state. So all I know, platinum +4 complexes, and let that one go, are always octahedral. Octa for short. Always. So, in these materials, each of which is a compound that contains an octahedral complex of platinum, because each of these materials contains platinum in the +4 oxidation state. Will have, each of these materials will have. Ammonia molecules has potential monodentate ligands and chloride ions as potential monodentate ligands. From this information, moles of ions per mole of compound, which is determined by simple solution conductivity observation. Or, how many moles of chloride ion can I readily precipitate by dissolving a mole of this compound in solution, or a mole of this compound in water solution, a mole of this compound in water solution. Know this, that the moles of silver chloride readily precipitatable per mole of compound, even though I got 4 moles of chloride ion per each mole of compound. The moles of readily precipitatable silver chloride diminishes as I go from compound 1 to 2 to 3. And we've already made arguments to support the conclusion that these coordinate covalent bond interactions are strong. So tell me, as moles of chloride ion readily precipitatable as silver chloride diminish, what do you think is happening as we go from compound to compound with chloride ion? Regarded, connected strictly by ionic bonding, or perhaps by coordinate covalent bonding? Do you think that when I get a chloride ion to be coordinated, it's more stable and more difficult to precipitate? Well, let's take a look at the first complex. N will represent ammonia, so I don't have to keep writing H3 all over the place. Moles of ions per mole of compound tell us when I dissolve a mole of this, I got 5 moles of ions in the solution. What are the 5 moles of ions? Well, it's 1 mole of this complex ion and 4 moles of chloride ion. So in a solution of this, I've got 4 moles of chloride ions swimming around. So when I dump in a bunch of silver ion, every one of these chloride ions reacts with silver ion and gives me a mole of silver chloride. Now look at the second compound. The only difference is 1 fewer moles of ammonia in a mole of compound. Now these are each platinum in a +4 oxidation state. Do you think from what we have considered so far that ammonia or chloride ions behaving as monodentate ligands, which one bonds more strongly with platinum? Ammonia. Now, you can put silver ion, but this isn't silver ion. But it was the case, for example, with cobalt in +3 oxidants. So for the second material, 4 moles of ions per mole of compound. And 3 moles of readily precipitatable silver ion. So I can conclude for compound number 2, 1 of the moles of chloride ion is complex. So what I should do now is to get familiar with writing formulas for complexes. When we write the formulas for complexes, we shall include the formula for such in brackets. Perhaps you've come to recognize that when I wrote formulas for these nickel tetracarbonyl materials and had brackets around the nickel tetracarbonyl. Here. Brackets, complex, whole complex. Here. Complex, showing 1 mole of chloride ion in the so-called first coordination sphere. This first coordination sphere is just a term referring to the complex itself. No more, no less. What ligands are in this first coordination sphere? Well, the formulas for these ligands will be contained within the brackets, as they're part of the active complex. Well, let's look at compound number 3. How many chloride ions in the first coordination sphere for this stuff? 4 moles of chloride ion, but only 2 moles readily precipitated. And again, I reduced moles of ammonia by, again, 1 mole. 6, 5, 4. And please, when you play this game, don't take this to mean a chlorine molecule. This is 2 chloride ions. This is not a chlorine molecule. This is 2 chloride ions. More formula recognition stuff that the uni students just have to get to know. So when I go back to my structural representation, my drawing, I gotta say, where's the second chloride ion? We'll let this green thing be a chloride ion. There's the complex I presently have on the board. Recognize if you have not yet recognized. An octahedron is a very symmetrical geometric figure. is more symmetrical than a trigonal bipyramid. Trigonal bipyramid's got 5 peripheral atoms or groups, octahedron 6. But still, an octahedron is a simpler shape. Why is that true? Because every geometric position of an octahedron, they're one and the same. But for a trigonal bipyramid, the top and bottom, the axial positions, are different geometrically than the equatorial in-plane position. How might I realize this? That an octahedron is a simpler geometric shape than a trigonal bipyramid. You hear this 72045? I hope. But forget that. How many bond angles are there for an octahedron? Provided all the peripheral atoms and groups are the same. Bond angles are not even. How many? How many bond angles? 90. And 180. That's it. For a trigonal bipyramid, how many bond angles? 3. Right off the bat, you see more bond angles of consequence. That tells you it's a geometrically more complex structure. All right, that's the question. Where goes this second chloride line? Well, the truth of the matter is, depending upon how I make this dichloral complex, the complex with the 2 chloride ions in the first coordination sphere, by synthetic cleverness, I can make this, where the chloride ions are at a right angle with respect to each other. This one is said to be cis. Write that on the board. Cis means, practically speaking, what atoms or groups are as close to each other as possible. Look at this chloride line. Which of these geometric positions are cis with this chloride line? Is this one cis? Is this one cis? Is this one cis? Is this one cis? Only this position is trans. I'll put it over here. See? Now I'm holding the complex like this. See? These 2 chloride ions are in this square plane, and I purposely cant this square to show you that this square is not in the plane of the drawing surface. This forward part of the square is projected forward. This rear part of the square is behind the drawing surface. You've got to get familiar with this stuff regarding drawing pictures. The only parts of this sketch which are in the plane of the drawing surface is the top group, the bottom group, and the atom or ion in the center, right there. This is not in the plane of the drawing surface. These 2 up in front, these 2 behind. Okay? I mean, see, I can rotate this and show you all these different cis orientation positions of the chloride ions with respect to each other. And all that amounts to is this thing being blown around in space by the wind. But, back to synthetic cleverness. Right? Under other appropriate conditions, with synthetic cleverness, I can make this. So, I got no names. This, cis. But if I operate on this in the laboratory, synthetically, and I remove this chloride ion and replace it with ammonia, and instead get the chloride ion here, now I have trans. I trust the word or prefix trans speaks for itself. Trans, a cross point, opposite. Cis closest, trans opposite. Okay? Now let's go to the laboratory and do some more synthesis. Now I'm going to operate on compound number 3. Turn it into compound number 4. been done, I turn the compound 3 to compound 4 by again removing 1 mole of ammonia from the composition of the compound. Where should these chloride ions be? Well, if I started with the 2 chloride ions trans, then the 3rd chloride ion has to go into a position which is simultaneously cis to each of these chloride ions. But if instead I started with the 2 chloride ions cis to each other, with synthetic cleverness, I can get the 3rd chloride ion to occupy a position which is cis to each of the 2 original chloride ions, like this. Not all like ligands are cis to each other. Formula for the complex. Moles of precipitatable chloride ion, readily precipitatable 1. Moles of ions per mole of compound. How many? Moles of ions per mole of compound. 2. Well, what do I do with respect to the name game? Over here, I can call the complex cis-dichloro tetraamino platinum 4 or trans-dichloro tetraamino platinum 4. What am I going to do with this thing? I suppose I could call this all cis. But when I got this thing, I got a problem. Because now I got like ligands which are cis and trans. So how should I name the daggone thing? I name it with respect to a spherical entity. Let's take the Earth. What's the general term for this line that goes around the middle of the Earth? I mean, the equator. What's the general term for any line that travels around the entire Earth? Meridian. Aha. Called a meridian. Now, circumference is also acceptable. Just like the equator is also acceptable. But the term we chemists take is meridian. Notice that in octahedron, because every one of these bond lengths is the same if all the groups are the same. An octahedron is perfectly inscribable in a sphere. So on the outer surface of this sphere, all like ligands will be contained. So when all like ligands are containable in this outer surface of the sphere, and containable in this construction that I make around the sphere, which has as its diameter one of these bond lengths, then I call this thing meridianum. So this thing is meridianum. More language. Well, what if I've got my light ligands all at a 90-degree angle with respect to each other? Well, let me get one more model out here just a second. Sure you've seen this model? What is important now? See this before? That's it. What is it? It's not octahedron, it's not the same model. Octa means what? 8. How many faces does this thing have? 8. Octa. What's hedron mean? What does hedron mean? Greek word hedron. Means face. It's got 8 faces. And for a perfect octahedron, each face is a perfect equilateral triangle. Geometric positions. 1, 2, 3, 4, 5, 6. And for what we just made, oh, here it is. All like ligands share the property of being on the same face, right? So we'll call it facial. Each of 3 like ligands lie on same face of octa compounds. A lot of words to say what the model shows at a glance. We'll pick it up from this point next.